All right, so let's finish up this last graph here before we move on to algebraically finding limits. So how'd it go? Part I, what was our limit as x approaches 1 from the left side?
-3.
Great, -3. And how about as we approach from the right side?
+4.
+4. So what's the limit as x approaches 1?
4 or 2.
Doesn't exist.
It doesn't exist. Remember, if our left and right hand sides don't match, then our limit does not exist.
The next one, that's when it's f of 1. That's 2.
You got it. So the actual value of f at 1 is 2.
Yeah.
All right, and then our last set, we're looking at 4. So we want the limit as x approaches 4 from the left side. Where are we going? That's an asymptote, so it's going to get closer and closer to that asymptote, but it's continuing to go down. So we are approaching negative infinity. And if we look at the limit as x approaches 4 from the right, we're approaching positive infinity. And since our left and right hand limits don't match, that means our limit as x approaches 4 does not exist. And what was the value of our function at x equals 4?
Undefined.
Yeah.
If we have a vertical asymptote, it is going to be undefined. Questions at all on finding the limit given a graph? Definitely going to see that on the take-home quiz. Definitely going to see that on the homework. Definitely going to see that on the exam. Definitely going to see that on your first exam in Calc 1.
The next thing that we're going to do is we're going to be finding limits using properties of limits. So any of you who have any background in calculus and, oh, you know all the tricks and this and that, well, we're not using the tricks in here. We're going to be doing everything by definition, no shortcuts. Those are reserved for calculus. Okay, so let's just talk about all these rules that we have. First rule is limit of a constant. It's the limit as x approaches a of some constant c will always be that constant. Now you'll see throughout this section that I end up writing like words over on the side because, I don't know, there's so many formulas and these limit rules, they get weirder and weirder looking that I frequently find it's easier to remember the words than the actual symbols of it. So the limit of a constant is a constant, and that should make sense for us because if our function f of x is a constant, then that means that the graph of this is simply a horizontal line, so the y value is always staying the same. So no matter which x value we're approaching, the y value is always the same, this constant value. So the limit as x approaches -2 of 1, since our function is a constant, our limit's going to be 1. Similarly, the limit as x approaches 7 of -5 is going to be -5. So the limit of a constant is always that constant. Next, we have the limit of the identity function rule. And the identity function is just y equals x. So it says that the limit as x approaches a of x is always a. And again, that should make sense for us because our identity function is y equals x. That's a line with a y-intercept of 0, 0 and a slope of positive 1. If we think about the graph of that, and if y is equal to x, whatever number x is approaching, our y value is going to be equal to that, right? We're hitting the points 1, 1, 2, 2, 3, 3, and so on. So we're basically just taking this and plugging it in for x, and then that'll be our answer. So the limit as x approaches 436 of x is equal to 436. The limit as x approaches 2/3 of x is just going to be 2/3. Any questions so far? All right, so now we'll get into some more involved rules. Suppose that c is a constant, a is a real number, and the limits as x approaches a of f of x and the limit as x approaches a of g of x both exist. So we have the limit of a sum rule. This says that the limit as x approaches a of two different functions added together equals the limit of the first function plus the limit of the second function. So it's almost, I always think of it like I'm almost distributing the limit to each of the functions. But I also remember it with the words, the limit of the sum is the sum of the limits. We want to find the limit as x approaches 6 of 8 plus x. This becomes the limit as x approaches 6 of 8 plus the limit as x approaches 6 of x. We're going to find each one of those limits individually and then just add them together. So what is the limit as x approaches 6 of 8?
8.
8. And then we want the limit as x approaches 6 of x. What's that?
6.
6. And now we just add these two together and we get a final answer of 14. Questions at all? Well, the same idea applies if we have a difference as well. That we're basically kind of distributing this limit in. The limit of a difference is the difference of the two individual limits. If we want to find the limit as x approaches -3 of x minus 9, this becomes the limit as x approaches -3 of x minus the limit as x approaches -3 of 9. So I'm not going to use the negative a second time because I put the minus in between the two limits. And then we evaluate each just like the previous one. So what's the limit as x approaches -3 of x?
-3.
And then the limit is x approaches -3 of 9.
9.
We get a final answer of -12. I like this next kind of problem a lot. I'm anxious to see what all I can find in my math lab for our exam. Because this way, those of you who know the shortcuts don't have the opportunity to use the shortcuts. It's more like having to actually use the rules. So let's suppose that the limit as x approaches 4 of f of x equals 10, and the limit as x approaches 4 of g of x equals -3. We want to find the limit as x approaches 4 of g of x minus f of x plus 6. We're going to start with these sum and different rules for our limits. And I'm basically distributing in my limit to each of those. We get the limit as x approaches 4 of g of x minus the limit as x approaches 4 of f of x plus the limit as x approaches 4 of 6. We'll find each one of those and add or subtract them. The limit as x approaches 4 of g of x was given to us. It's equal to -3, so we just plug that in. The limit as x approaches 4 of f of x, also given to us. It's 10. And then the limit as x approaches 4 of 6. We know a limit of the constant is just that constant. And now we just need to add or subtract. We get -7. Questions at all? Our next rule is the limit of a product rule. Here, if we have the limit of two functions multiplied together, then we can rewrite that as the limit of the first function times the limit of the second function. So the limit of a product is the product of the limits. Again, we're kind of distributing this product in. So there's also another rule that's not in our book, but it's in the calc book, and I think it's appropriate to show it now. It's the constant multiple rule. If we're taking the limit as x approaches a of some constant times a function, you can take this constant and bring it out in front. Kind of like with our log rule, right? We had a log property where if it was an exponent, we brought it out in front. So I think of it kind of like that. But the reason that this works out is it's just an application of the rule before. So if I have the limit as x approaches a of 3 times f of x, well, that's the same as saying the limit as x approaches a of f of x, right, 3 times. And that limit of a product rule says, okay, well, make that the limit as x approaches a of f of x times the limit as x approaches a of f of x times the limit as x approaches a of f of x. We have the same thing multiplied together 3 times. So it's 3 of those limits. So that's how you can just bring it out in front. All right, so then we have a limit of a power rule as well. So if the limit is x approaches a of f of x raised to the n, so, and that n is inside the function, like inside with the limit. Like the limit is x squared. They're simply saying that this can be the limit of x and then take your answer and square it. And since a radical can be rewritten as an exponent, this rule expands to our radicals as well. The limit as x approaches a of the nth root of f of x, well, you can just find the limit as x approaches a of f of x and then take the nth root of that. So let's suppose that the limit is x approaches 4 of f of x is 10, and the limit as x approaches 4 of g of x is -3. We want to find each of these limits, and there are 4 of them. I think I'm going to break you guys out into some breakout rooms and let you work on these for a few minutes. Now, it's important that you write out all your steps. I'm definitely going to want to see all the steps written out on your take-home quiz. And then I'll bring you guys back in, I don't know, 5 minutes.
Oh, my videos.
There we go. Here, I'll scroll up fast or slowly so that everybody can see the answers since we forgot to turn the video back on. Oh, so I also have a correction. I don't know what I was thinking when I was writing this. I was like, I don't like this. Okay, my explanation here was so wrong on this last property. What's wrong with me? Okay, so I'm going to apply the limit of the product rule before, which means that this is going to turn into the limit as x approaches a of 3 times the limit as x approaches a of f of x, and we know that the limit of a constant is always that constant. So that's how come the 3 is out in front. You ever talk sometimes and it's like, as you're talking, you're like, this doesn't sound right, but I'm going to go with it. So sorry, here it is. This is the correct explanation on why that 3 comes out in front.
I did that when I was tutoring somebody. Had to go back and re-explain everything.
Yeah, it happens to the best of us. Okay. So anybody questions on any of these rules so far? All right, so when I give directions like on the take-home quiz or something, it says show all the steps in big bold letters, that's what I want you to be doing, what we were just doing. Now I'm going to show you how to combine some of them. So there'll be one on the quiz where I want you to show all the steps. But other than that one, you can use these techniques that we're going to learn that kind of does a little more combining. All right, so the limit of a monomial rule, if we have the limit as x approaches a of b sub n times x to the n, that's going to be equal to b sub n times a to the n. All right, so b sub n is just some coefficient. It's not a variable, it's just some kind of real number. And the only reason they put a subscript on it is because in a polynomial, you have a bunch of monomial terms strung together. That's what makes it a polynomial. So they just use that subscript on the coefficient to distinguish between the different terms in a polynomial. Basically, all you're doing is the same thing we did with our limit of the identity, where you just took the a and you plugged it in for the x. That's really all that's happening. The only difference is we're just taking our a and plugging it in for x. It's kind of skipping over this rule right here. So if we want to find the limit as x approaches -2 of 5x squared, we're just plugging -2 in for x and cleaning it up. 5 times -2 squared. The limit is 20. And that should make sense for us. We know that the graphs of polynomial functions are continuous. So the limit is going to be, since we know there's no holes or jumps or anything weird happening, the limit is just going to be whatever the corresponding y value is. So we just plug it in. Now we have the limit of a quotient. Oh, the limit as x approaches a of 2 functions divided by itself. It's just the limit of the one in the numerator divided by the limit of the one in the denominator. So again, we're kind of just distributing this limit to everything inside the parentheses. Of course, we're always concerned about the limit of the denominator being equal to 0. So the limit of the quotient is the quotient of the limits, provided that the limit of the denominator is not equal to 0. All right, well, that means that we can break this up into the limit of the numerator. Because there's so many terms, I like to put it in parentheses. Over the limit of the denominator. And to find each one of these limits individually, we're just plugging it in, right? It's just an application of this limit of a monomial rule, because we got a bunch of monomials. I think we could take the time to rewrite it and distribute the limit to each one of these and then do each one individually, but that's a lot. So I'm going to plug in. What's this? -8 plus 8 minus 1 over 5 plus 6 cleans up to be -1 over 11. If we would have gotten a 0 in the denominator, we would have had to do something else. And I'll teach you what to do about those things. Sometimes the limit doesn't exist. Sometimes we can't rectify the 0 in the denominator. Questions on these last couple examples? All right, well, we've had a bunch of rules, and now we're going to put them together in a theorem. We know theorems are much more powerful, the most powerful that we have in math. This theorem says that f is a polynomial or a rational function, and a is in the domain of f, then the limit as x approaches a of f of x is equal to f of a. So basically, if you have a polynomial or a rational, as long as what you're approaching is in the domain, the limit is just what you get when you plug that number in for x. Which again should make sense. We talked that polynomial functions are smooth and continuous. We know that rational functions are not necessarily, but as long as we're in the domain, like the different sections of a rational are always nice and smooth and continuous. So let's find some limits here. I'm seeing if there's another theorem here, because the first one right out of the gates is a trigonometric, but it's true as well. That theorem applies to trig functions as well. As long as what you have is in the domain, all you have to do is plug that number in for x and you're good. Well, cosine we know is a nice, smooth, continuous function. So all we're doing is plugging pi in for x. So this is going to become cosine to the third of pi, and we know that's the same as cosine of pi cubed. What's cosine of pi?
-1.
-1, and when we cube that, we get -1. Questions, anybody? All right, next up we have the limit as x approaches 6 of x minus 5 over x squared minus 4x minus 1. Our theorem said that we can just plug in the 6 as long as it's in the domain of our rational function. Usually I just plug in first, and then if there's a 0 in the denominator, I address it. I guess you could factor it and see if that's in the domain first if you wanted to. This one doesn't factor. But if we plug in 6, I'm going to get 36 plus 24 minus 1. That's not going to be 0, so we should be safe to just plug it right in. So 1 in the numerator, 36 plus 24 minus 1 gives us 59 in the denominator. Questions? Next, we want to find the limit as x approaches 3 of x squared minus 9 over x minus 3. What do you notice this time when we go to plug 3 in?
Is it 0?
There's a 0 in the denominator. But before we just say, the limit doesn't exist because I have a 0 in the denominator, you want to try to do some algebraic manipulation to try to simplify this to eliminate the problem of having a 0 in the denominator. Notice that this rational expression can be factored. In the numerator, we're going to have x plus 3 and x minus 3. And then we can simplify these x minus 3's. And now we're looking at the limit as x approaches 3 of x plus 3. And now that's safe to plug in for. So I'm just plugging 3 in. And we get a limit of 6. If you think about what's happening here, like with the graph of this, because we have a common factor, what does that tell us regarding this rational function?
There's a hole.
There's going to be a hole there. So the graph of this actually just looks like a line with a y-intercept of 0, 3 and a slope of positive 1, because the simplified version tells us what the graph of this looks like, but we're going to have a hole at negative 3. So a function can be undefined at a particular x value, because this is absolutely undefined at 3. It is not in the domain of the function, but the limit is not what's happening exactly at that x value. The limit is what happens is we get really, really close to it. So that's why we can just simplify it so that our problem's gone, creating the 0 in the denominator, and then using our limit laws from there. And as we look at the graph here, clearly the limit as x approaches 3, way out here, is 6. Questions at all? So I got a couple here that are a little bit tough that I'm going to break you guys out to work on. So this first one, I'm going to get you guys started though on the algebra. So this first one here, if I plug 0 in for x, I clearly have a problem because now I have this 0 in the denominator. So we need to try to fix that. We want to do algebraic manipulation to simplify this. Notice what we have is a complex fraction. So to deal with this, you want to simplify the complex fraction by multiplying by the LCD. Now hold on though, don't be working on it because I'm going to put you in groups. And then the next one, same deal. We're going to have a problem because when I plug this -2 in, I'm going to get the square root of 9, which is 3, minus 3, which is 0 in the denominator. Another problem. So what we want to do with this one is rationalize the numerator. I'm sorry, the denominator. All right, so I'm going to put you in groups this time. I'm going to do it right. And I'm probably going to give you it's like 10 minutes to work on this because some of this algebra can be a little tricky. But you can do it. It's really not any algebra you haven't done, right? This is the hardest part about calc, is remembering all our algebra techniques and applying it to the calculus. So I think the key is I have to hit open all rooms here. So, all right, I'll see you guys in 10 minutes.
So here we are halfway through the next example. All right, so our denominators, we're multiplying those conjugates. So multiplying the first two together, we're going to get x squared plus 5. And then multiplying the second two together, we're going to get minus 9. That's the limit as x approaches -2 of x plus 2 times the square root of x squared plus 5 plus 3. And in the denominator, that's going to be x squared minus 4. Who sees the end? What should we do?
X minus 2 in the denominator and x plus 2, and then simplify x plus 2.
That's just it. Because notice if we go to plug this in for x, we still have a problem. We still have 0 in the denominator. So we have not done enough. That denominator is the difference of two squares that can be simplified. I mean, that can be factored. And then ultimately we can simplify this rational.
Because we have the x plus 2 on the top and the bottom, so that means there's a hole there.
Yeah. Full of this awful thing. I don't know. You know what? I don't know if this would classify really as a rational. I mean, it is because we have a variable in the denominator, but typically we define a rational function to be a polynomial in the numerator and a polynomial in the denominator, and a square root is not a polynomial. So yeah, there's going to be a hole, but it's not going to, necessarily look like what you think it's going to look like. And now it's safe for us to plug that -2 in for x because it's going to give us a -4 in the denominator and not a 0. So let's plug in. Under our radical, we're going to have 4 plus 5, so that's the square root of 9. Six over -4, which we will simplify to be -3/2. Questions at all? All right, let's do one more. There's 2 more in this section. I'm going to do this one, and then we'll start class on Wednesday. I'll put you guys in groups.
Are there going to be some of those last ones on the homework then?
Like these ones? Sure.
I feel like I need more practice with them. So
Yes,
that's good.
yes. And a lot of times these limit ones, and even when you first start getting into calc and doing all these derivatives, you do need to do a large volume of problems. That I know historically that has not been my philosophy to you guys, like, oh, just do a bunch of problems. That I've always kind of preached, study your procedure, but you need to start doing a large volume of problems just because you know so much algebra at this point. And any of those techniques can just pop up in the middle of any of these calculus problems. So you really do need to do, 40, 50 problems in a section just to make sure that you have seen every single possible algebra trick that they could throw up. I remember that I think that the reason one of the reasons I failed calc those first couple times was because they told me to do every odd one in the book. And I'm like, yeah, right. And it wasn't until I actually started doing every odd one in the book that I was successful, because you just got to practice so many of them. And remember, you can also always pull up the ebook in My Math Lab. So if you feel like there hasn't been enough in the homework, you can just pull up the ebook and go to the end of the section, and there'll be tons of them, and you can pull them out. All right, so these last two are piecewise functions. Like I was saying, I'll do this one today, and then I'll start class on Wednesday, putting you guys into groups, and you can do the second one. All right, we want to use our limit properties to find the indicated limit or state that it does not exist. They're asking us to find the limit as x approaches 2 in our 3 parts, but you'll notice that that's right where our piecewise function splits, right? X less than 2 and x greater than 2. Now, if they were asking us to find the limit as x approaches 0, it'd be no issue, because we'd just be using the top function and we would just plug it in like normal. But because the limits that they're asking us for is where our piecewise function is split, we got to do the left and the right hand limits. My pen doesn't want to write all of a sudden. Okay, well, maybe I lied. Since my pen doesn't want to work for me right now, and I'm going to have to close out OneNote and start it up, we'll just end right here today, and we will do these two on Wednesday. Does anybody have any questions about anything before we leave today? Yeah, and sorry if I missed you in office hours. Like I said, I don't know. I thought if I went in that other way that it would be the right meeting, but it was not.
Do you have the office hours tonight?
Yes, ma'am.
Okay, thank you.
Okay, it sounds like I will see several of you this evening. All right, sounds great. Have a wonderful day.
Thank you.
Bye.